In this question, we have one rope at a 15-degree angle, something like this, and a second rope at a 10-degree angle, something like this, and we have our performer hanging from these two ropes, like so. We have been asked to find out the tensions in these two ropes, knowing that the performer has a mass of 76 kilograms. So there are three forces acting on her. There is the weight pointed down. There is this tension, which is over to the right, and there is this tension, which is over to the left. I'm going to call this tension T1, the one over to the left, and this tension T2, the one over to the right. So this is now her entire free body diagram. Let us now draw in the origin and axes. The origin is always on our character. That's her there. And here's the x-axis, and here's the y-axis. Now, the angle of T2 is 10 degrees. That's easy enough to say because that just corresponds to what we had in our picture. The angle for T1 is a wee bit more involved. We know that this angle over here is 15 degrees. So with a little bit of geometry, we can say that this angle over here must also be 15 degrees. Or, with respect to the x-axis, it has to be 15 plus 90 is equal to 105 degrees. So now we have two forces that are oblique. Let us break these down into their components. T2 has a horizontal and a vertical component. T1 has a vertical and a horizontal component. So for T2, we could say that this side, the vertical side, is opposite this angle. So that is going to be T2 sine 10 degrees, because this is the opposite side of the 10-degree angle. And this horizontal side would be T2 cos 10 degrees. On the other side, this over here now becomes the opposite side of the 105-degree angle, so this becomes T1 sine of 105 degrees. And this side over here now becomes the adjacent side of the 105-degree angle. So this is T1 cos 105 degrees. So now we have established all of the forces and we've broken them into their components. Now let us start analyzing these different directions. Remember that since T1 and T2 are two unknowns, we're going to need two equations to solve out for what they could be. Let's start with the x direction, because that has only two components in it. In the x direction, the total force is going to be given by, the rightward force is T2 cos 10 degrees, and the leftward force is T1 cos 105 degrees, which we could write like this. And that total force is equal to mass times acceleration. So that means that T2 cos 10 minus T1 cos 105, or cos 105 is going to wind up being negative in any case. So correctly speaking, I should keep this absolute value sign here. is equal to mass times acceleration. But we can simplify this a little bit because our heroine is not moving. So that means that there is no acceleration in the x direction. This entire right side goes to 0. Now, let us solve for what information we know. The cosine of 10 is 0.984, or 985, let's say. So we could write this as 0.985 t2. The cosine of 105 is negative 0.259. So let's write the second term as negative 0.259 t1. And the right side, of course, was equal to 0 because the acceleration is 0. So I can move this to the other side, and we would get 0.985 t2 equals 0.259 t1. Then divide both sides by 0.985, and we get negative, or since we've moved it, it would be positive, 0.263. T2 is equal to 0.263 T1. So this is the first relationship we have between these two tensions, that T2 equals 0.263 times T1. But this is one equation and two unknowns, so we're going to have to look at what happens in the y direction. Now for the y direction. In the y direction, the total force is the sine component of T1 pointing upwards plus the sine component of T2 also pointed upwards minus the weight. But total force is also equal to mass times acceleration. So we now have that T1 sine 105 plus T2 sine 10 minus weight is equal to mass times acceleration. Once again, our heroine is not moving in the y direction, so that means that her acceleration is 0. Now, what about her weight? Her weight is equal to mass times gravity. Her mass was 76. Her gravity is 9.81, which works out to 745.56. So now, let's take this information and plug it into this equation. Now, in the meantime, we can also solve for some of these trigonometric values. So the sine of 105, that's 0.966. And the sine of 10 is 0.174. Minus the weight, 745.56, is all equal to 0. Let's simplify this somewhat. I can move the 745.56 to the other side, but we can also use the expression for T2 that we solved for earlier. Remember that we'd written T2 in terms of T1? We had shown that T2 is equal to 0.263 times T1. So 0.966 times T1 plus 0.174 times 0.263 times T1 is equal to 745.56. (0.966) plus 0.174 times 0.263 gives us 1.012. So 1.012 times T1 is equal to 745.56. So dividing both sides by 1.011, we get 736.87. 0.89 rather. So T1 equals 736.89. And since T2 was equal to 0.263 times T1, that's 193.8. So T2 is equal to 193.8 newtons. So the tension in this left rope is 736.89, and the tension in the right rope is 193.8. In this question, we have a ball which is dangling from a rope which is attached to the ceiling. The angle that the rope makes with the horizontal, or rather the vertical, is 35 degrees, which interestingly enough is also going to mean that the angle of the rope with respect to the ball is also 35 degrees. So let us draw the free body diagram for this ball. The weight is going to point down, and the tension must point in the same direction as the string. Therefore, that encompasses all of the forces in this question. So now let's draw our axes. I'm going to set my x-axis in the conventional way, and my y-axis also in the conventional way. This angle is 35 degrees, which means that this angle has got to be 90 minus 35 is equal to 55 degrees. Now, since the tension is at an oblique angle, we need to break it into its components. The horizontal component would be given by tension cos 55 degrees, because this is the component that is adjacent to this angle. And the component that is opposite this angle would be T sine 55 degrees. Now, let us work out what are all of the forces taking place in the y direction, because we were being asked to find what was the tension in the rope and the acceleration of the ball. To find the tension of the rope, the easiest way to do that is to analyze y. So let's start with that. I should actually say the only way to analyze the tension in the rope is to start with y. That's why we have to start with that. And the reason for that is because the tension has to balance out the weight force, so we can work out the tension that way. We were told that the mass of the ball was 0.02 kilograms. In y, the total force is given by T sine 55 pointed up plus the negative weight force. But total force is also equal to mass times acceleration. So we can say that T sine 55 minus the weight force is equal to mass times acceleration. Now let's solve for the weight. Weight is equal to mass times gravity, which is equal to 0.02 times a gravity of 9.81. So that's going to work out to 0.1962 newtons. This is the quantity that we now put in for weight over here. So we now have T sine 55, I don't know what sine 55 is off the top of my head, 0.819. So 0.819 is sine 55 multiplied by the tension minus 0.1962 is equal to the mass of this object, 0.02, times the acceleration in the y direction. But this ball is not accelerating upwards or downwards. Its motion in the y direction is 0. Its acceleration in the y direction is also 0. So this cancels out. 0.819 tension is therefore equal to 0.1962. So 0.1962 divided by 0.819 is 0.2395. Let's call that 0.24. So the tension in this string is 0.24 newtons. The next step is to solve for the forces in x so we can find the acceleration in x. In x, the total force is given by t cos 55 degrees. But again, total force is equal to mass times acceleration. So that means that t cos 55 degrees is equal to mass times acceleration. Now, the tension was 0.24. Cos 55 degrees is equal to the mass, 0.02, times acceleration. Now let's go ahead and solve this. 0.44 cos 55 is 0.1376, and then divided by the mass, which is 0.02, we get 6.88. So this here, the left side was 0.138 is equal to 0.02 acceleration. So the acceleration was 6.88 meters per second squared, and more specifically, it would be in the I hat direction because the acceleration is in the x direction. You've probably seen an effect like this. If someone has, let's say, some object dangling from their rear view mirror in their car, when you accelerate, that object starts leaning back. That's exactly the same effect as this. The object is being accelerated by the string, by the tension in the string, and to provide that acceleration, the string has to lean backwards. And the acceleration of the car, the acceleration of the object that results, is going to be caused by that horizontal component of the tension. That's what's going to pull our object forwards. In this question, we have a person who is pushing on a 45 kilogram ice block. They are pushing downwards and to the right. This is an icy surface that they are walking on. The coefficient of static friction is 0.1, and the coefficient of kinetic friction is 0.03. So, what we would like to do is we want to find out, first of all, what is the minimum force that our hero needs to exert in order to get it moving, and once it has started moving, what is the acceleration going to be? So, let's start by drawing a free body diagram. There's the object, there's the ice block, it has weight pointed downwards, normal force pointed upwards. The force applied is down and to the right, something like that. And we were told that the angle of the push was 25 degrees below the horizontal. And opposing, so if this is the direction of the push, opposing the direction of motion, because this is going to slide rightwards, is the force of static friction. Static friction is going to point leftwards. Okay. Those are all of the forces. Let's now draw in the axes. We can set these in the conventional way. And we will break the applied force into its components, since it is the only oblique force here. So this y component would be the sine component, Fa sine of 25 degrees, or more correctly I should say negative 25 degrees because it's below the axis. And this over here would be the cosine component, Fa cos negative 25 degrees. So now we have broken this into its two components. We're now ready to analyze the directions and the forces in each direction. Now, because this is a case where we have static friction, we have to find out what the normal force is before we can start applying anything that involves the static friction, which means we need to solve the y direction first. In the y direction, there are a total of 3 forces. There's the normal force pointed up, there is the weight force pointed down, and there is the force applied, the sine component of that also pointed down. And all of that is going to be equal to ma according to Newton's second law. So simplifying and combining these two equations, we get normal minus weight minus the applied force sine negative 25 degrees. I'll write it like this, is equal to mass times acceleration. Now, the object is not collapsing into the ground, and it's not levitating off the ground. So there's no motion at all in the y direction. And that means that there's no acceleration in the y direction either, which means this acceleration is 0. So the next thing we need to do is to find out what the weight is. Weight is equal to mass times gravity. So the mass was 45 kilograms, gravity 9.81. And let's see what that's equal to. 45 times 9.81 gives us 441.45. So that's the size of the weight. And while we're at it, we can also say what sine of 25 is, or rather sine of negative 25. It's negative 0.422. So combining everything that we have here, we say the normal force minus the weight, which is 441.45, minus 0.423 when we round it appropriately times the applied force must all be equal to mass times acceleration, which we already said was 0. So simplifying this even further, we end up with normal force is equal to 441.45 plus 0.423 times the applied force. So we're going to hold on to this equation over here. And now we're going to look at what happens in the x direction. Now let's take a look at what's happening in the x direction. In the x direction, the total force is equal to the force pointing rightwards, that's Fa cos negative 25 degrees, minus the force that's pointing leftwards, that's the force of static friction. But, of course, total force is equal to mass times acceleration. So we can say that the applied force times the cosine of negative 25 plus the negative static friction is equal to mass times acceleration. Now, if we've just started moving this, then that means that the acceleration is infinitesimally greater than 0. Another way to phrase this question is to ask, what is the push that you need to provide, the maximum push that you can provide such that the acceleration is still 0? In other words, what is the maximum push that can be countered by static friction? To solve this, we will set acceleration to 0, which means, again, this entire right side becomes 0. And then let's solve for static friction. The maximum value of static friction is going to be given by static friction is equal to mu s multiplied by the normal force. So, mu s we were told was 0.1, and the normal force we know is 441.45 plus 0.423 applied force. So multiplying all of this across, we get that the value of the static friction must be 44.145 plus 0.0423 times the applied force. Now, let us take this value of static friction and let us plug it in over here. When we do, we get the applied force cosine negative 25 degrees minus this entire expression, which is 44.145 plus 0.0423 applied force is all equal to 0. Okay. What is the cosine of negative 25? 0.906. So simplifying this still further, we get 0.906 times Fa minus 441.45 minus 0.0423 Fa applied force is equal to 0. Let's keep simplifying this. Subtract 0.0423 and we get 0.864. And we can also move the this should be a 44.1. We'll move the 44.1 to the other side. So that gives us 0.864 times applied force is equal to 44.145. So last step, 44.145 divided by 0.864 gives us 51.09 newtons. So this is the minimum value of the applied force that needs to be given in order to provide the acceleration, or rather in order to overcome the force of static friction and to accelerate this from rest. I just realized I wrote meters per second squared here. I don't know why I did that. It's a force. It's supposed to be in newtons. Now, the next part of this question asks, once we have started pushing it with an applied force of 51.09 newtons, what is going to be the acceleration that results? Remember, now we have started it from rest, which means that we are no longer in the realm of static friction. We're now in the realm of kinetic friction. So that means that technically we would need to redraw our free body diagram. The normal force would stay exactly the same. The applied force would stay exactly the same. The weight force would stay exactly the same. But this time, the friction force would be very different, because now we have kinetic friction, not static friction. Now, let us draw in our origin and axes as before. While I'm going to be very strict on myself for drawing this out, I'll forgive you if you didn't draw a second free body diagram for this question. The orientation of the forces hasn't really changed. The only thing that's changed is that what used to be a static friction has turned into a kinetic friction. And while that is an important change in the physics of the question, it's not going to affect the free body diagram except to turn Fs into Fk. So, now let us break the applied force in the same way as before. So this is the opposite side. It becomes applied force sine of negative 25. And this being the adjacent side, this becomes applied force cos negative 25. All of the forces in the y direction are precisely the same as what they were before. So now we just need to figure out the forces in the x direction. In the x direction, the total force is going to be given by the applied force, or the cosine component of the applied force, more correctly, plus the negative kinetic friction. And all of this is equal to mass times acceleration. So now we have Fa cos negative 25 plus the negative Fk is equal to mass times acceleration, and we're looking for the acceleration. Now, to solve for Fk, since we already know Fa, we need to apply the formula. Fk is equal to mu sub k times the normal force. So mu sub k, for ice on ice, the coefficient of kinetic friction is 0.03. But the normal force we have not yet worked out. The normal force is equal to 441.45 plus 0.423 times Fa, which we said was 51.09. So, let's work this out. 51.099 multiplied by 0.423 plus 441.45 is 463.06. So this all works out to 0.03 times 463.06. which is 13.89. So that's the size of the kinetic friction. So applied force, 51.09, times the cosine of that angle. Cosine of negative 25 is 0.906, as it was before. Minus the force of kinetic friction, which would be 13.89. That's equal to the mass, 45 kilograms, remember? Times the acceleration. By the way, this should be a positive 0.406. The cosine of negative 25 is positive 0.406. So 51.09 multiplied by 0.906, and then subtract 13.89 for the friction, we get 32.41. And then divide by 45 for the mass, we get 0.72 meters per second squared. So this works out to 32.41 is equal to 45 times the acceleration divided by the distance by 45. You get an acceleration of 0.72 meters per second squared. And this would be an I hat. In this question, a person is dragging a 45 kilogram block using a rope. The angle of the rope is 25 degrees, and there is a coefficient of friction between the ice block and the ground. The coefficient of static friction is 0.1, and the coefficient of kinetic friction is 0.03. And we want to find out what is the minimum force this person must pull with in order to get the ice block moving, and what acceleration would result once it has started moving. So what is the minimum force required to overcome static friction? And if you keep applying that force, what acceleration will result now that we are in the realm of kinetic friction? Let's draw the free body diagram. The weight force will point down, the normal force will point up. The applied force is coming from the rope, and since it is a rope, we shouldn't call it an applied force anymore, we should call it a tension. And finally, there is the force of static friction. Now, let us draw our axes. So the angle of the tension is 25 degrees above the horizontal, and we can break it into its components like so. So this vertical component is going to be T sine 25 because it is opposite the angle. And this horizontal component is going to be T cos 25 because it is adjacent to the angle. Now, let's start analyzing what is taking place. Let's start with the y direction because we have a static friction here. We need to follow the y direction first. In the y direction, we know that the total force is going to be normal plus tension sine 25 minus the weight. But total force is also equal to mass times acceleration. So that means that normal force plus tension sine 25 degrees minus the weight force is equal to mass times acceleration. Now, this object is not going to be moving in the y direction. It's not collapsing into the ramp, and it's not levitating off the ramp. The acceleration is 0. What about the weight force? The weight is equal to mass times gravity. Mass, 45. Gravity, 9.81. Now, 45 times 9.81, you can use your calculator to solve for that. 441.45. So that gives us the normal force plus T sine 25 degrees minus 441.45 equals 0. The sine of 25 is 0.423. So I'm going to move this 441.45 to the other side. That gives us normal plus 0.423 tension, or better still, let me write it like this. Okay, normal plus 0.423 tension equals 441.45, or equivalently, that the normal force is equal to 441.45 minus 0.423 times the tension force. So this is our first relationship that we have between these two unknown quantities. And we are going to save that for our work in the x direction. Now let's look at the x direction. In the x direction, the total force is equal to T cos 25 degrees minus the force of static friction. But total force is also equal to mass times acceleration. So that means that T cos 25 degrees minus the force of static friction is equal to mass times acceleration. Now, if we've only just managed to get this moving, then we are applying a tension which is just large enough to start this moving, to just overcome the force of static friction. So that means that this force is just infinitesimally bigger than this force. We can basically solve for what that threshold tension has to be by setting the acceleration to 0. Now let's solve for the static friction. Static friction is equal to mu sub s multiplied by n, which works out to mu sub s, 0.1, times a normal force, 441.45, minus 0.423 tension, which will simplify to 44.145 minus 0.0423 times tension. This is now the expression that we plug into static friction. So T cos 25 degrees minus 44.145 minus 0.0423 times the tension is equal to 0. Let's simplify this somewhat. The cosine of 25 degrees is 0.906. So now this can be simplified to 0.906 times the tension minus 44.145 plus 0.0423 times the tension is equal to 0. So now let's add 0.0423 and we get 0.949, let's call it. move the 44.14 to the other side, and we get 0.949 times the tension is equal to 44.145. So that gives us a tension, which is equal to 0.145 divided by 0.9486, which is 46.54. And this would be measured in newtons. So this now is the tension that is required in order to start this 45 kilogram object moving. The next part of this question asks what would happen if this were to start moving. Well, once it starts moving, the normal force and the weight force are going to remain the same. The tension force, however, and actually the tension force is also going to remain the same. It's still oriented at this 25 degrees, but the friction force is now going to be much smaller. Why? Because now we're in the realm of the smaller kinetic friction. Once something has started moving, it's easier to keep it moving than it is to start it moving. Now, let us draw in our axes. That's the y-axis. And that's the x-axis. Once again, we would break this down into its two components. I'm being rigorous over here, but I'm not going to take off any points if you didn't draw a second free body diagram, just this once. So this over here would be the tension cos 25, and this one over here would be the tension sine 25. Now, knowing this information, let us solve for the acceleration in the x direction. We already know there's going to be no acceleration in the y direction, so I'm not going to bother recalculating the normal force or the weight force. So in the x direction, we have a total force, which is given by t cos 25 minus the force of kinetic friction. Now, T cos 25 minus kinetic friction is going to be equal to the total force, but total force is in turn equal to mass times acceleration. So we now have T cos 25 minus the force of kinetic friction is equal to mass times acceleration. Now, what's the force of kinetic friction? Force of kinetic friction is equal to mu sub k multiplied by the normal force. So let's first solve for the normal force. The normal force is equal to 441.45 minus 0.423 times the tension force, which was 46.54. For 41.45 minus 0.423 times 46.54. 421.76. So this is the size of the normal force. Now let's plug that in and find out what the size of the kinetic friction is. The size of the kinetic friction is the coefficient of kinetic friction, 0.03, times the size of the normal force, which is 421.76. 12.65 newtons. So now we have tension cos 25. We'll just recalculate that. Cos 25 is 0.906. So tension times 0.906 minus the friction, 12.65, is equal to the mass, 45, times the acceleration. We've already solved for the tension. It's 46.54. So 0.906 times 46.54 gives us 42.18. So 42.18 minus 12.65, that gives us 29.53. And dividing both sides by 45, we get an acceleration of 0.66. And this would be in the I-hat direction. So now we've solved for the acceleration of this object if it is feeling a tension of 25 degrees, and if we keep applying the same force, the same tension force after we have started it moving. Now, an interesting thing here is the acceleration when you have this tension above the horizontal was less than the acceleration when the tension was below the horizontal. That is not an obvious result, because if the tension is below the horizontal, the normal force would go up to compensate. It's a little bit like if I have this calculator and I press down on it, that's going to make it harder to drag it, right? Because the normal force has gone up, and therefore the friction force has gone up. So if this had been below the axis, like this, the normal force would go up, the friction force would go up, so the applied force must also go up to compensate and to overcome this greater friction force. But because we are giving a greater applied force, that also yields a greater acceleration in the case where we were below the axis. In the case where we're above the axis, the normal force is less, the friction force is less, so therefore the applied force, or the tension, the thing that's actually causing it to move, is also going to be less, but that also produces a smaller acceleration than what resulted when we were pushing it down into the ice the more inefficient way.